Hello and welcome back to High Peak Education. I would like to perform a total mechanical equilibrium problem using torque and forces. So let's have a look at this problem here. It says a uniform horizontal beam of length 8.00 meters and weight 200 newtons is attached to a wall by a pin connection. Its far end is supported by a cable that makes an angle of 53 degrees with the horizontal. See figure. So here's the pin connection, and here's this 53-degree angle with the cable. If a 600 Newton weight man, so there's the man, stands 2.00 meters from the wall, find the tension in the cable and the force exerted on the wall by the pivot. Okay, so let's go through this problem sort of one piece at a time. Let's first start off with writing down our knowns. Okay, and let's also carefully label our diagram. So it says a uniform horizontal beam. Now uniform is important because that means the center of mass of the beam is exactly at half the length of the beam. Okay, so if we call the length of the beam here capital L 8.00 meters, then the center of mass of the beam is at L divided by 2. Okay, and we also know what L is. So L is 8.00 meters, and then L divided by 2 would just be 4.00 meters. Okay, let's keep moving. And then we also know the horizontal beam has weight 200 newtons. So weight of the beam is equal to 200 newtons. Let's see, it's attached to the wall by a pin connection. So that there could be pin forces. Okay, so we'll have to consider that. And let's see, its far end is supported by a cable. So the thing is, there's probably going to be a tension force in the cable. And we don't know what that is, nor do we know the pin forces. And let's see, it's that angle is 53 degrees, so that's theta is 53 degrees. So here's theta. And we also know that there's a 600 Newton weight man, so the weight of the man is 600 newtons, stands 2 meters away from the wall. So why don't we call this distance right here x, that the man is standing away from the wall. Okay, so x is equal to 2.00 meters. And we're going to find, again, the tension of the cable and the force exerted on the wall by the pivot. Okay, so I think that there could be forces here at the pivot. That's at the pin connection. All right, so let's perform each of these forces as sort of a separate vector with a separate color. Let's start with red, and let's go ahead and start with the beam. So the beam is this W, weight of the beam. So I think that's at the geometrical center of the beam. So that's somewhere about here. Something like so. Okay. So the beam is 200 newtons. So that's definitely not the largest force, but let's go ahead and put that on there. This is the weight of the beam. Okay. Then we also want to look at the pin connection. Let's put that in blue. Now here's the deal. Listen carefully. The pin connection, we don't know much about it. I mean, there could be a vertical force, there could be a horizontal force. We don't really know. In fact, if the cord pulls back against the wall, there's probably a force in the x direction, so there could be a pin connection force. So since we're very uncertain about the pin connection force, why don't we call this right here FP x, that's the force of the pin in the x direction, and let's call this right here FPY. That's the force of the pin in the y direction. By the way, we keep referring to x and y directions, so it's a good idea for us to establish some axes. Okay, so this is the positive y-axis, and this should be the positive x-axis. And the far end is supported by a cable, and that makes an angle, and that we were thinking about the tension force. Okay, so this is the tension force, And again, that's separate from these pin forces. Those were in blue. Okay. So it looks like F pin X is a question mark, and F pin Y is also a question mark. But now let's go ahead and, I almost got ahead of myself, label this tension force. So this tension force goes up here from the end, something like so. So it goes along the cord. That's the tension force. And that tension force has this angle associated with it. Let's see. So we'll deal with that in a moment. And then how about the weight of the man? Well, the man stands here. So he has a certain weight. So let's put his weight vector down here. And he's 600 newtons. That's 3 times as long as the weight of the beam. So something like this. So here's the weight of the man. Okay. And I think that labels all our forces. And notice that X is labeled. So L is labeled. That's this distance here from the pivot to the end of the beam. L over 2 is labeled. That's this distance. And again, this is X, and I think everything else is labeled. Okay, now one more thing. We haven't chosen where our axis of rotation should be. Because I think that for total mechanical equilibrium here, we need to have some semblance of where the torque radius equals 0. So let's think about this. It seems the most sense that the radius should be 0 here at the pin. And let's think about why that is. First of all, if there were any problems out here, we'd expect that this beam was probably going to actually rotate at the pin. But notice that the pin has forces possibly in the Y and X direction. So if we make this radius equal to 0, the torques from those pin forces are both 0, and it makes the problem much easier. So we say set R equal to 0 meters at the pin connection, because this makes the torque equation easier. So this right here is the rotation axis. And again, this is R equals to 0. And by the way, notice that then X and L over 2 and L are all just positive radii in some sense. So when it comes to the angle phi for torque, we can consider the angle phi for many of these objects. Notice that for the man, I think the radius goes outward, the force goes downward, so phi for the man should be just 90 degrees. Okay, and we know the sine of 90 degrees is 1, so we'll just omit that from the torque equation. What about the beam? Well, the beam is having a weight downward and the radius is to the right. So since the weight is in the negative y direction and the radius is in the positive x direction, I think this is also 90 degrees. So the idea is that we're going to have, let's see, sine of 90 degrees is 1. Okay. Then let's think about this tension force. So we don't need to worry about the torques from the pin connection because that's radius equal to 0. But how about from the tension force? Well, remember, phi should be the smallest angle between the radius and the tension force. Now in this case, phi I think should equal theta. So that should be 53 degrees. Well, how do I know that? Well, it turns out that you can imagine this component here, which is like the y component. In fact, I'll probably even just go ahead and show that over here on the left side. So if the tension force is something like this, we have two parts to the tension force. We have the tension force in the y direction, and then we have the tension force in the x direction. So notice that in the y direction, that's Ft sine theta. This is theta. And then in the x direction, it's Ft cosine theta. Notice it's only really the Ft sine theta that's the perpendicular part to the radius. And that's the part that really contributes to the torque. So that's why 53 degrees is appropriate. Now, by the way, one more thing. We should decide which of these torques are positive and negative. Let's go in the reverse order. Look at this tension force. That's positive this way. The radius goes out. The tension force goes upward. That's out of the page. That to me looks like it's counterclockwise. So this is a positive torque. Next, let's think back to the beam. So the radius goes to the right, the weight goes down. We do R cross product with the weight force. The thumb points into the page. That's clockwise. That means this is a negative torque. And then lastly, for the man, the torque should be, I believe, also negative because the weight is down, the radius is to the right. And so R cross F, the force being the weight, is like so. Okay, so we've talked about the torques, we've talked about the components. Now we finally need to write down our equilibrium conditions. So I think we're really going to need 3 equations. We're going to need the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the torques. Okay, so let's take each of these one at a time. Equation 1, equation 2, and equation 3. Remember, equation 1 and 2 make up what we call equilibrium condition 1. And then equation 3 is equilibrium condition 2. Okay, so in the x direction, I think the pin has a possible force in the x direction. So that's F pin x. Let's call that a positive. By the way, if it ends up being a negative, it means the pin actually pulls to the left. But for now, since we don't really know, let's just call it positive. And then the tension force should be to the left. So we can see it's to the left in the negative x direction. So that's minus Ft times the cosine of theta. And as long as we're in equilibrium, this should exactly equal to 0. Okay, how about in the y direction? Well, in the y direction, I think the tension force is upward. What else is upward? Well, the pin. I mean, again, we don't really know if it's upward or downward, but let's just call it upward in case it's upward. So for symmetry, let's start off with pin. So let's do F pin in the y direction. Then we'll do plus tension force in the y direction, that's Ft sine theta. And then we need to consider the forces that are downward, that are negative. So I think we have the man and the beam. So that's minus the weight of the man and then minus the weight of the beam. And again, as long as we're in equilibrium, this must equal 0. Okay, that's equation 2. Lastly, the torque equation. Now the pin does not enter into the torque equation because the radius is 0. But we should take these torques. Let's do positive torques first and then negative torques. So the positive torque, we said, should be the tension, but only the tension force in the y direction. That is the sine component. So this is going to be, what is the radius? Well, the radius is just L. And then we need the force, so that's the tension force. And then its component that's perpendicular, that's sine of theta. Then we need the torque by both the man and the beam. So the torque by the man, we said, is a negative, and that's at distance x. And then the force is the weight of the man. And then, remember, it's phi is 90 degrees, so that's all we need. And then for the beam, we note that the distance is L over 2. And we note that it's the weight of the beam. Okay, and then again, because we're in equilibrium, the sum of the torques must equal 0. Okay, so notice we have 3 equations. Now let's think about our unknowns. I think that there are 1, 2, 3 unknowns. The pin force in the x direction, the pin force in the y direction, and the tension. So there are 3 equations and 3 unknowns. So this is a linear system. This can be solved. Now, by the way, we should think about a plan of attack. So since we want to solve this, we need to think about which equation is probably easiest to solve. Now, because of the convenience of the torque equation, that we could choose where the rotation axis was, I think the torque equation will be easiest to solve. Because notice that the tension force is unknown in the torque equation, but that's the only unknown in this equation. So I think we can solve that because everything else is known. Notice the pin forces and the tension forces are unknown in equations 1 and 2. So it's going to be easiest to solve probably equation 3. So let's write down what our strategy is going to be on the next board. So our strategy will be the following. Okay? We will say, for convenience, solve the torque equation 3 for the tension force, then substitute into equation 1 and 2 to find the pin forces. Okay, so that's what we're going to do. Now, by the way, I think we should just rewrite equation 1, 2, and 3 with all the negatives moved over, because that'll just look easier, and then we'll go ahead and solve. So let's do our best to recopy these equations. And by the way, I'm switching to the black color because now we're just doing algebra. The colors were meant to show you the directions and the vectors, but now we're on to the algebra. So now we're on to the solving. So let's go ahead and do, I think equation 1 becomes F pin in the x direction is equal to Ft cosine of theta. What's the second equation become? Well, it becomes F pin y plus Ft sine theta equals weight of the man plus the weight of the beam. And the third equation, that is the torque equation, becomes, let's see, Lft sine theta equal to x times the weight of the man plus L over 2 times the weight of the beam. All right, so let's see if we can solve equation 3. So let's solve this equation for tension. So the tension force, I think we need to divide by L sine theta. So this is x times weight of the man plus L over 2 times the weight of the beam, all divided by the length of the board, or the length of the beam, times sine of theta. So let's put the numbers in. We have the following. X, which was the distance the man was out, that's 2.00 meters. The weight of the man was 600 newtons, plus, now L over 2 is 4.00 meters, because that's half the board length. The weight of the beam was 200 newtons. And then we divide by L, and that's 8.00 meters. Sorry, 8.00 meters. Sine of 53 degrees. So this will be the tension force. So let's get this tension force. So with the calculator, let's perform alpha F1 to get a fraction stack, N over D. So let's do 2 times 600 plus 4 times 200. The calculator does not care about significant digits. And then divide by 8 times the sine of 53 degrees. Let's make sure we're in degrees, by the way. Let's go mode. Make sure we're in degree mode. We are, so that's good. Let's hit enter. Okay, so let's write this down. We got about 313 newtons, rounded to 3 significant digits. So this is 313 newtons. Okay, now that we have the tension force, I think we can now return to equation 1. So, equation 1, with a tension force here, We just need to divide by cosine to get the pin, or sorry, multiply by cosine to get the pin force. So the pin force in the x direction should just be 313 newtons times the cosine of 53 degrees. So let's get this pin force in the x direction. So we need 313 newtons multiplied by the cosine of 53 degrees. That gives us 188 newtons, again rounded to 3 significant digits. All right. And then finally, we want the pin force in the y direction. So the pin force in the y direction should be weight of the man plus the weight of the beam, this time minus Ft sine theta. So let's put those numbers in. The weight of the man, we already talked about that before, that's 600 newtons. The weight of the beam, we discussed that before, that's 200 newtons. And then minus Ft sine theta, so that's minus 313 newtons times the sine of 53 degrees. Okay, so let's get this pin force in the y direction. Calculation shows 600 plus 200 minus 313 times the sine of 53 degrees. So we get 550 newtons. Let us write this down. 550 newtons. Notice the pin force in the x direction was positive and the y direction was positive. So if we start to label some of these with their colors that we did before, the tension force, that was this one, 313 newtons, that supports the beam. That one is not extremely large because it's at such a large radius. It gives a large torque. But notice the pin forces are both positive, so the pin force in the x direction is indeed in the x direction. Okay, so that's in the positive x direction, that's here, and then the y direction, it is indeed upward. So the pin, to create static equilibrium, holds the beam and the man and the weight of the beam itself upward and pushes out to the right. Okay, so that ends this problem. Hopefully you learned something about mechanical equilibrium and some of forces equal to 0 and some of torques equal to 0. So thank you very much for your attention. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please leave a comment if you would like. I look forward to reading them. And I will see you in the next video. Thank you for watching High Peak Education.